Alright, I'm trying to make a change in the way I record. Hopefully you won't notice a difference in audio quality, but I know those crazy blue things are showing up on the screen and I'm trying to get rid of them. So hopefully this will work. We'll find out, won't we? Okay, so first of all, we want to talk about differentiability so you can get through the worksheet, and power rule, which is really exciting because this is the first rule you're going to learn. So you're going to get into a whole bunch of rules. Actually, I have an app for that. Let me show you. I think I wrote this at a past time when I was teaching calculus back in like 2013. So you don't need this now, but this is just to help you learn your derivatives. So you're like, oh, I think sine goes with cosine. So you just click sine and cosine, and if it's a match, it stays that way. And you just, well, let's see if you know these. You probably don't. But it's a good refresher if you already took calculus in the past. If you have not taken calculus in the past, then I do not suggest that you try this yet. Alright, I'll give you that link later. Once I've taught you the derivatives, and then you can use that to kind of drill yourself, to remind yourself of the rules. Okay, so we want to talk about differentiability so that we can start building up our collection of rules. And then once we build up our collection of rules, we're going to learn how to combine the rules. So it's really cool. We're going to spend a lot of time ramping up on this derivative stuff. Okay, but before we do, we want to be absolutely sure we know what functions can be differentiated. And so that you can answer without knowing the rule. So, in order for you to be able to take a derivative, okay, so I'm finding this is probably the easiest way to describe this. You want to know if a function is continuous at the specific point you want to take the derivative, p. So first of all, it has to have a limit from the left, limit from the right, and the value of the function has to be the same. We've discussed that before. But now we have the definition of the derivative in hand, and so we want to make sure that the limiting tangent line there is in the same direction from both directions. So in this case, we want to make sure that, think about it as you got a little car driving. This is what I want to think. There's a little car driving, and it's carrying a piece of wood up above. This wood attached to the top of the car. And as the little car is driving, that piece of wood isn't going to make a sudden jump. That piece of wood is going to smoothly move around. It's okay if we don't define the derivative here, because this is the process by which we do define the derivative here. We're just saying as this car goes around this direction, once it gets to that point, that wood's going to be in the same place as if the car were driving backwards. Okay? So let me give you an example of where this doesn't hold true. What if you have this kind of function, like a mountaintop, where there's like not a rounded mountaintop, but the little car can't get over that. The person walking maybe can just step over that little bump, but the car needs to have this be not only a continuous function but a differentiable function, because otherwise the car, because really the two wheels are kind of like a plane right there. You can't really go over this. The car is going to get stuck on the top, and so that car is going to be stuck in midair. There's no derivative defined here. So the function itself is continuous. So f is continuous. F is continuous but not differentiable at p. Okay? And so anytime you have continuity but not differentiability, is because the slope changes rapidly at that point. Okay? So that's what we need for differentiability. It's a continuity plus definition. Continuity plus the derivative that you're defining is also continuous. I guess I should give you a piece of language to go with that. If you have a function that comes to a point, I usually call that a corner. If you have something that looks like this is a cusp, this is still not differentiable. Someone may argue that the at a cusp, the derivative is going infinite from both directions, but in one case it's going positive infinity, in the other case it's going negative infinity, and we do make that distinction. So it is your derivative is not, it does not exist at the cusp point. Okay, and we talk about a tangent as an example in this homework, and we have not talked about tangent yet. We reviewed sine and cosine, but we did not review tangent. So tangent, here's what tangent looks like from 0 to 2 pi. Remember, tangent is sine over cosine. So how would we plot that? Well, if we remember what sine looks like that from 0 to 2 pi. Cosine looks like that from 0 to 2 pi. So just draw yourself a little sketch to remind you. But if tangent has sine over cosine, the important part is, whereas cosine equal to 0, we need to get our asymptotes in there. So we got our asymptotes in there for sine. They look like this. And they continue there if you want to do two or four periods of this thing, because we're going to find out pretty quickly the tangent cycles twice as fast as our other trig functions. Okay, so what about cosine near the origin? Cosine near the origin is just 1. So really, really close to the origin. Tangent is going to look exactly like sine. And that's going to happen again when cosine is 1 over here and 1 over here. And then it just actually is going to do the same thing later. But what's going to happen is you're going to get an asymptote, ding, 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 ding. Okay? So you're going to get this kind of thing happening. So that's what tangent looks like. So, yeah, so that's pretty much all you need. If you know that, then you can do the exercise in the worksheet. So we will bring up more trig review as we need it. And again, there's a whole video I gave you earlier in the semester as an optional video. If you feel like, oh gosh, I don't remember this stuff, go back and watch my trig review videos and it'll all come back to you. Okay? I think that's all you need for this exercise. I do want to say, however, when we really use the inverse of tan, what we tend to do is just look at this little piece from minus pi over, oh gosh, what was that? Pi over 2 to pi, minus pi over 2 to pi over 2, and then that's the thing we flip around and use. But for this exercise in the worksheet, I'm assuming you're trying to invert the whole thing, which you can't do. So you should say that that function is not invertible because I did not specify what the restriction would be. If you don't specify a restriction on one of these repeating functions, then you can't invert it. Okay, so now is the big thing for the day. This is the big exciting new reveal, if you haven't heard it before. And I want to bring some things together that we've already done. So we've already shown, by using various tools, we've shown things like this, maybe not this exact thing. The derivative of x is 1 because, well, that's easy because it's just the line y equals x and the slope there is 1 all the time. So that's not a hard one. F prime, whoa, I should do it f prime. I should do it like this. This would make way more sense. What I just did made no sense. Okay, the derivative of x squared we found is 2x. The derivative of x cubed is 3x squared. And the derivative, well, I think we probably didn't go beyond that. We did show that the derivative of 1 over x is minus 1 over x squared. And we also showed that the square root of x has a derivative minus 1 over 2 square root of x. What I want to do is I'm going to ask you to rewrite these. I'm going to ask you to actually pause the video and do this. The first few are going to be easier than the other ones, but for everything in this chart, I want you to write it as x to some power. So even 0, or even 1, x to the 0 is 1. I want you to take every piece, so the first 3 just carry over, but I want you to do the last 2, so these we get for free, okay? But I want you to rewrite those last 2, so pause the video and rewrite those. Okay, so what we wanted to do is we want to rewrite 1 over x as x to the negative 1, and then that means the derivative is minus x to the minus 2. We're rewriting everything so that we don't have fractions or square roots, anything like that. So if you didn't know what I was talking about, maybe now it's clear. Do the last one if you didn't do it already. Okay, so these formulas, are these derivatives, are the first examples of what's known as the power rule. And the question should come up, hey, if this works for these examples, what is it that just happened? Well, it looks like maybe the following is true. If f equals x to the n, is it true that the derivative is n times x to the n minus 1? That's what it appears to be, right? So there's an unseen 1 here that popped down. Is this true? So I want you to pause for a second and ask yourself if that rule is true for at least the 5 examples on the screen. See, all that time you were asking why I'm forcing you to do these derivatives by hand, and the biggest reason in my mind is to motivate the power rule. And the power rule is something that will be your friend for a very long time. My guess is that 20 years from now, after you're done with calculus, if you never take calculus again, you'll still remember the power rule. That's the one thing people tend to remember. And but I hope you remember a few more concepts. But this seems to be the thing that sticks with you because we use it over and over and over in the class. And so so I want you to just let this sink in and make friends with it, and then ask the following question, like, if that's true, can we take the derivative of other stuff that way? What about x to the 1/3, which is the cube root of x? Is it possible that the derivative of the cube root of x is 1/3 x to the what? Negative 2/3. Yes, it's true. It's true. And I think it's a little bit crazy because these guys we can prove outright using the definition. And these guys are a little more nuanced. And so at this point I'm asking you to trust me that this is actually true, but these you don't have to trust me. These we just proved. But I'm asking you to trust me that you can make this leap, that you can do this as long as, n does not have to be an integer. N can be r. It could be any real thing, with kind of one exception. There's an exception, and let's talk about that exception. Okay, let's just do these examples. Okay, so anything to the 0 is 1, so I'm writing 1 as just x to the 0. The derivative of 1 is 0 because this is y equals 1. The derivative of that is clearly 0. The derivative of x is 1. The derivative of x squared is 2x, and the derivative of x cubed is 3x squared. So that's clear. All right, if we want to take the derivative of x to the negative 1, we're going to get minus x to the negative 2, and we take the derivative of this guy, minus 2x to the minus 3, and this is minus 3x to the negative 4. Everything I've written here is true, and so we can kind of ignore the fact that there's a missing case, right? What about the fact that, so if we rewrite these back into our everyday notation, and then we notice somebody is missing, and that's all I'm going to say. I'm going to leave this as a mystery because this guy, the derivative of 1 is 0. Okay, it's not 1 over x. But then what happens to 1 over x? What if we have 1 over x here? Then what is f? And I think we either did that already or we're going to do that soon. That was one of your homework exercises, to kind of just look at that. Actually, I think I told you already about that. I think I think I let the cat out of the bag for that. But I want you to think about that. Why is this guy missing anyway? And this kind of thing can keep you up late at night. And if it does, it's totally okay, because this is really cool. The fact that 1 over x doesn't show up in this family is pretty cool. But I will give you a clue towards it. I will give you one more rule. If the function is e to the x, it is its own derivative. Okay? And there's no exceptions, there's no other functions that work except, say, like y equals 0 is its own derivative, and variations on a theme. Like if I say 2 e to the x, when I take the derivative, I get 2 e to the x. But that's just the same as e to the x. That's really just an extension of that. So at its baseline case, e is that special base for which, and e is about 2.718281828, whatever. It does not repeat, but those 4 digits make it sound like it's going to repeat. But anyway, e to the 0 is 1. And the derivative here is 1, so I should have drawn it more like this, I guess. Okay, so that's a magic rule that you can just get for free, and we will continue talking about all this stuff on the next video.